Pharaohs rover team is an undergrad students team at the Military Technical College from Cairo, Egypt. It's our second time presenting in the URC. 40 students from different departments working together to build the rover. The rover now ready to challenge everything in the task. The team is divided into 5 main groups: mechanical, electrical, science, financial, and the media group.
The mechanical team decided to build a skid steering with bogies to ensure that there are 6 wheels touching the ground at any moment. This achieves high stability, mobility, and the maximum benefit from the motor's traction. The 2 bogies connecting the front and the middle wheels are non-symmetric, that to improve the obstacle crossing capability. Also, we enhanced the rear suspension mechanism to permit an independent movement for the rear wheels to withstand the impact during the 1 meter drop task. We used aluminum alloy 70-75 in most of the design to gain high strength with relatively low weight.
For wheel section, we showed our tendency to use Linux to generate off-road wheels, but we faced problem with the weight, so we decided to use airless foam wheel and to avoid air leakage problem caused by the tough environment. Each wheel's hub connects between the wheel's rim and the bogie, so that the rover's weight will be supported on the wheels themselves rather than the motor's shafts. Also, the selected motors are small to be in wheel motors to ensure its safety.
We develop our arm with 5 degrees of freedom: base, shoulder, and elbow rotation, and 2 degrees of freedom in the end effector. We improve our arm to use a heavy-duty linear actuators instead of gearboxes to reduce weight and improve the capability of the arm to lift heavy weight up to 5 kilograms.
The control system is based on NI Myreo embedded system, which is programmed using LabVIEW. The control system is divided into 2 main modes: manual mode and autonomous mode. In the manual mode, the rover is controlled manually from the control station. First, we started controlling the rover using multi-axial joystick. Then, we altered the control system to be controlled using a steering wheel. The control algorithm is based on fuzzy control system, where its inputs are the data from the steering wheel and its outputs are the velocities of the right and left speed of the motors. In the autonomous mode, the rover either moves to a specific preset point, as in astronaut assistance task, or whenever the connection to the rover is lost. This system is also designed using fuzzy control system. This system has 2 inputs: the distance between the rover and the destination point, the error in the heading angle of the rover to the destination point.
The communication system consists of two different FCC accepted links. The first link is the Wi-Fi network, consists of two outdoor routers with 15 dBi antennas to guarantee high data rate for easy transmission and reception of video signals from cameras which is mounted on the rover. The second link consists of extend transceiver as a data link for control and navigation signals. We designed and implemented a helical directional antenna to achieve high gain and high directivity. The antenna is designed to operate at 2.4 GHz. The proposed antenna design is simulated on CST Studio Studio. The antenna is implemented in cylindrical dielectric which is made of Teflon with diameter 3 cm and it's only about 46 cm long and can easily be constructed from ordinary and low-cost components. For monitoring, wireless IP cams will be used to provide a real-time video for rover actions and movements. In addition, an ultra-wide view cam will be used for high definition and panorama photo required in sample return tasks.
The robotic arm is totally different from the last year. It was developed to cover the last year defects. Its coherence control was developed using inverse kinematics. The kinematic model of the robotic arm was developed using MATLAB Robotic Toolbox. In order to make the control easier, two constraints were added to the solution of 3-degree freedom arm, so our arm is able to move in straight lines even vertically or horizontally regardless of its previous configuration. These two modes of motion help us in completing different computation tasks, such as equipment service and astronaut assistant tasks. Finally, the arm has two modes of control, either joystick or slow lab view GUI, in order to deal with any unexpected situation.
our science cache task, we have two main sections, the on-rover test and the station test. The on-rover test. The rover will search for appropriate locations for sample, take multiple samples, test some on board for the presence of proteins, lipids, and carbohydrates. The rover will be provided with a sticky paper and a magnet to have an idea about dust composition. The rover will also have a magnet and a sticky paper to have an idea about the dust composition. The sensors will be on board to check atmospheric composition and soil condition.